SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of this lecture is Mobility Management in MEC. MEC full form is Mobile Edge Computing. So, let us see that in mobile edge computing. So, again MEC stands for Mobile Edge Computing. So, this is then edge computing applied to the mobile networks. To take the advantage of edge computing in the applications, thereby providing more efficiently the resources to the applications which are running on the user equipment, that is with the mobile handsets. And second important thing is that applications will be benefited out of the latency. So, a new kind of applications are possible to run in this particular scenario. So, let us see that mobility, that means that how the mobility is also enabled or ensured while the edge computing is enforced. So, that is called the mobility management in MEC. Now, in the conventional mobile cellular network, the mobility of the user is enabled by handover procedure. So, you can see through this particular example that if you have the user equipment and this is another user equipment and you have the base station, let us say A, and you have another base station, let us say B. Now, if this user equipment 1, this is 2, if the user equipment moves means he is a mobile, he is a person who is moving, and it comes into the range of that base station B. So, this particular state will be changed from A to B as it comes in this range of the service. So, this place where this particular state is changed from the base station A to base station B for ensuring this particular mobility is handover. So, in conventional mobile cellular networks, the mobility of the users is enabled by the handover procedure. So, there is a procedure called handover procedure, and due to this particular procedure, this mobility is properly maintained. When the user equipment changes the serving ENBs as it roams throughout the network to guarantee the service continuity and quality of service. So, once he moves from the serving ENB or SCENBs as he roams and comes into the different serving SCENBs for service. So, it has to guarantee the continuity of the applications, that is the service continuity and quality of service, that is the applications which are running ensures also the continuity of the service and also ensures the quality of service requirements. So, if the user equipment offloads the computation here, for example, if offloads here on the edge server, so here let us say that this is the edge server. So, if it offloads to the edge server, offloads computation to MEC, then it is important to ensure the service continuity. So, as he moves, so all these service continuity has to be ensured, how that we are going to see. So, there are several solutions mobility of UEs. One is that we have to see about the mobility of the UEs. So, mobility low mobility UEs means to adopt the transmission power of SCENB or ENB during the time when offloaded application is processed by MEC. Second is high mobility UEs, that means if UE performs handover to the new serving ENB or SCENB despite of the power control. The service continuity may guarantee by virtual machines migration. So, if let us say that this is a virtual machine which is running this application. So, VM migration will happen, so that in a new MEC or MEC at the SCENB, let us say B, will also allocate this particular VM migration and continue to run, and therefore, this ensures for a high mobility user equipment this particular continuity of the service. So, the process during which the virtual machines run at the current computing node is migrated to another. So, more suitable and the computing nodes or by selection of a new communication path between user equipment and the computing node. So, what is that particular selection criteria for virtual machine migration? This is going to be an important factor in the high mobility user equipments, whereas it is to be offloaded, it adopt the power of ENBs during the time when the offloaded applications are being processed by apps. So, there are two different scenarios that we are going to consider here while discussing the mobility management in MEC. So, let us see about the power control. So, in case of UEs, mobility is low and limited when user equipment or the user equipment are slowly moving inside a building. A proper setting of the transmission power of the serving and or neighboring SCNBs can help the guaranteed the QoS. So, take this particular example that if let us say that user equipment moves with a low under this particular category called low mobility or mobility is low of a user equipment, then it has to adjust the power, that you can see that it has to increase the coverage by some power control. So, this is considered in the cloud aware power control algorithms, helping to manage the offloading of the real applications with the strict delay requirements. The main objective of the CAPC, that is cloud aware power control, is to maximize the amount of offloaded applications processed by MEC with a given latency constraint. Now, this is achieved by adaptation of the communication of the transmission power of SCNBs, so that the handover to a new SCENB can be avoided if possible, while moving the user equipment remains connected to the same SCNB as the transmission power is increased. So, power control will help in avoiding the handover here in case of low mobility. Let us see the virtual machine migration when the user equipment is moving at a mobility is not means mobility is high. If the user equipment mobility is not limited and the power control is no longer sufficient to keep the user equipment at the same serving ENB and SCENB, a possibility to initiate the virtual machine migration should be contemplated in order to guarantee the service continuity. And so, this is the condition, either it is a high mobility case of user equipment, or if it is, let us say that power control, if the mobility is such that that power control is no longer sufficient to keep the UE at the same SNB, then it has to be migrated. Then it has to initiate the virtual machine migration to guarantee the service continuity and QoS requirement. So, these are two important factors to guarantee the service continuity and QoS requirement. There is a need for virtual machine migration. So, therefore, we are going to consider the virtual machine migration under these two situations. Now, on one hand, the virtual machine migration can increase the cost, that is called cost of virtual machine migration. Representing the time required for VM migration and backhaul resources spent by the transmission of VMs between the computing node. On the other hand, there is a gain if the virtual machine migration is initiated, called gain of due to the virtual machine migration. Since the user equipment can experience lower latency and backhaul resources do not have to be allocated for transmission of the computation results back to the UE. So, therefore, there is a gain. Now, without the VM migration, a probability that UE is connected to the optimal MEC decreases with the increasing number of hops between the UE and ENB. So, take this particular example, that if the user equipment is moving to another location and serving base station vicinity is now changing from SCENB A to SCENB B. So, continuing here, serving from A will no longer be the optimal if it is still connected to the same SCENB A without the migration. So, this particular aspect that is called optimal MEC is violated or it decreases with the increasing number of hops between UE and ENB where the service is. This results into the increased delay. So, that it will increase the delay. Why? Because if it is moved to this position and is still being served and is still, if it is moved and is still being served, for example, if it is being served from A. So, the number of hops will be more and the delay will be more here in this case, more delay compared to if it is being served over here, if it is being served over here. So, this results into the increased delay if the decision is not to migrate or continue to be connected. So, contrary, the connection of UEs to the optimal MEC results in the lowest delay, but at the high cost of migration. So, if the migration happens, then cost will be more, but the delay will be reduced to a lower level. So, the reason of this phenomena is that VM migration should be ideally initiated after each handover performed by user equipment to keep the minimum delay. Now, let us take this example that for virtual machine migration why it is needed. So, when user equipment exploiting MEC 1, so you can see that user equipment is exploiting the MEC 1, this virtual machine is being run by to run user equipment 1, user equipment. Exploiting the MEC moves from ENB 1 to ENB n, this one moves from here to here, while conventional radio handover is performed whenever UE crosses cell boundaries, the VM migration is initiated after the handover to ENB is performed, since the cost of M is less than the gain. So, here you can see that the cost of M is greater than the gain. So, no migration is done when it passes through ENB 2. Here in case this particular ENB 3, what you can see that the cost of migration is more than gain. So, no migration is done in ENB 2 and ENB 3, whereas here in ENB n, what you can see that the cost of migration is less than the gain. So, virtual machine migration is happening. So, this is a perfect example that will decide that if the user equipment is moving even with different handover, it is not going to do a virtual machine migration. So, virtual machine migration will happen only if the cost is more than, if the gain is more than the cost. So, in virtual machine migration, we can design the proper decision policy determining whether to initiate the virtual machine migration or not. So, this is to balance the trade off between the migration cost and the migration gain. So, the problem would be then to find an optimal threshold policy when the migration is initiated. Consequently, after each handover to a new ENB, the optimal threshold policy decides whether the virtual machine migration should be initiated or not. Such an optimal policy should always achieves the maximum expected gain if compared to never migrate strategy, that is, the computation is located still at the same MEC and the scheme when virtual machine migration is performed after a certain specific number of handovers. So, let us summarize what we have discussed here in this virtual machine migration cost. So, therefore, we have to treat the balance, the trade off between the migration cost, that is cost M, and the migration gain, that is gain M. Now, for that it requires to find an optimal threshold policy to deal with this threshold. This optimal threshold policy will decide when the virtual machine migration is initiated. So, this particular optimal threshold policy decides when the virtual machine migration should be initiated or not. So, such an optimal threshold policy always achieves the maximum expected gain if never migrate strategy, that is, the computation is located still at the same MEC and the scheme when migration is performed after a specific number of handovers. So, this is going to be an important policy, that is called optimal threshold policy here in achieving the low latency at all points of movement, that is mobility. Now, let us see FMC service migration. For efficient service migration in a particular paradigm which we have seen, FMC of MEC, that is follow me cloud. So, FMC follow me cloud is a particular MEC architecture that we have covered, in the previous lectures. So, under this particular MEC architecture called FMC, that is follow me cloud, we are going to see that we are going to analyze this service migration. So, under this FMC there is a trade off to achieve between the cost of service migration and maintaining the good user experience. So, here what we see a trade off between the cost of service migration and the good user QoS. So, the service migration decision is taken based on this trade off between the migration cost and the user QoE. Such a decision making the process, such a decision making process is often modeled using a Markov decision process. Here we have to now deal with a Markov decision process for this particular decision based on to see this particular trade off, that is the cost of migration and the quality of service for the user. So, the agents in Markov decision process model decides whether a service shall be migrated to an optimal data center or not when concerned UE is located at a certain known distance from the current DC. So, here in FMC model follow me cloud has two main component, namely FMC controller and DC and GW mapping entity. Let us understand the model and then we will look into that particular trade off, how using Markov decision process we can model this particular trade off and evolve a decision whether to migrate or not. So, FMC model has two main component, one is called FMC controller. So, if you can see over here, FMC controller is this central entity and DC and GW, that is gateway mapping entity, data center and the gateway mapping. So, here you can see that there is a data center over here, there is another data center over here and data center 1 that is in the distributed mobile network, there is another data center and another data center. So, let us see this particular mapping which is called service gateway and service gateway and so on. So, let us go ahead and see this particular mapping of a DC and the gateway mapping entity. So, these can be either two independent architecture components or a functional lumped into one and can run as a software on any of the data centers of the underlying. In this architecture, the cloud network here and the mobile operator network like this are distributed. Here you can see that they are distributed, they are not centralized, both are distributed. Now, data centers are mapped to a set of PDNs and GWs. So, PDNs and GW, that is the gateways, that is the data anchor points in EPS based on some metric, that is location or the hop count. So, this mapping may be static or the dynamic. So, here you can see that DC and GW mapping is shown over here. Now, this exchange of network topology information is essential over here in case of the migration at is contribute to the estimation of the migration cost. In case of dynamic mapping, the topology information is exchanged between FMC service provider and mobile network operator. Alternatively, MNO entity could be in charge of updating FMC service provider with such information either reactive or in a proactive. It is assumed that FMC controller entity exists for managing the distributed DC instances. Alternatively, a distributed DC can coordinate among themselves in a self organizing network. Let us summarize. So, there are two types of methods which we are now going to consider about the mapping. One is called static, the other is called dynamic. So, this mapping of data center with the gateways, with the service gateway, and service gateways are now serving these customer or user equipments, and user equipments are moving here, you can see in this particular scenario. So, if they are moving, so they are coming in the service gateway range of that particular data center. So, this particular mapping of a service gateway to the data center is going to be decided whether it is mapping to be done in a static manner or in a dynamic manner. If it is in a dynamic manner, then topology information also required to be exchanged among each other, so that this particular aspect can be identified about the mapping. Now, FMC service migration is required when the user equipment changes its data anchor gateway, that is P gateway relocation. So, changing the data anchor gateway also causes the change of UE's IP addresses and the change of IP address noticed by the corresponding data center. So, in the event, the preliminary decision has to be taken by user equipment or the current data center on whether the service migration is worthwhile or not. So, the decision may be taken on the following factors. First is the service type. So, for an ongoing video service with a strict quality of service requirements may be migrated. The other type of thing is called content size. In case the user was watching a movie and the movie is about to finish at the time of this data anchor gateway relocation, UE may decide that FMC application layer not to initiate the service migration. Third factor is the task type of service. In case the machine type communication, sessions of emergency warning, delay sensitive reporting have to be always migrated to the nearest data center. So, the service migration decision to migrate or not relies on several criteria that depends upon the user expectation on the service, that is QoS or QoE cost and the network cloud provider policies at each data anchor gateways, relocation events and load balancing events. So, there are many complex factors which are involved that we have discussed here in FMC service migration. So, once it is deemed appropriate by either the user equipment or the current data center to migrate the service, the FMC plugin available at the data center may request the FMC controller to select the optimal data center with the right service and the right content to serve the UE in its new location and to initiate the service migration. So, this is simple procedure how the migration is to be initiated and how that is to be performed. So, as a service may consist of multiple cooperating sessions and the pieces, the decision has to be made indicating whether the service has to be fully or partially migrated, and that is while considering the service migration cost, like cost associated with the initiation of a new virtual machine at the target data center, cost associated with the release of the resources at the source data center, and the cost associated with the bandwidth consumption due to the traffic to be exchanged between the data center and FMC controller. So, all these are the cost factors while considering the service migration, and then an estimate of the cost to be possibly incurred shall be compared against the benefit to the cloud in terms of traffic distribution and also to the end users in terms of quality of experience. So, service migration is hence initiated based on the trade off between the total estimated cost and the benefit resulting from possible service migration. So, in the next section we shall look how the service migration procedure can be modeled through a Markov decision process. So, Markov decision process, it is possible to derive the optimal policy that can be employed to decide to migrate or not a service. So, let us summarize here what we have covered here in this particular FMC service migration. So, FMC service migration requires various cost factors to be incurred while the migration, and that has to be taken into account to decide whether to migrate or not. For the continuity of the service from that specific SC, E and B. Now, this particular aspect requires that the cost shall be then incurred shall be compared with the benefits to the cloud in terms of traffic distribution and also to the end users in terms of quality of experience. So, therefore, there is a trade off between the total estimated cost between the total estimated cost for the migration versus the benefits resulting from the possible migration. So, this particular aspect to decide whether to migrate or not is how the service migration procedure can be modeled as, therefore, it is modeled as Markov decision process problem, and this Markov decision process problem will then derive an optimal policy that can be employed to decide whether to migrate or not the service. So, let us see about the MDP formulation for FMC service migration. Let ST be the process describing the evolution of the system state, and capital S denotes the state space of the MDP. In order to derive the state space, it is assumed that 3 GPP is divided into hexagonal cells, whereby each cell belongs to a tracking area TA and each tracking area belong to a service area, which is served by one SGW, that is the service gateway connected to the packet gateway. Okay, so, this is what we can explain you, that let us say that this is the hexagonal cells, this is again another hexagonal cell. So, this particular area is divided into hexagonal cell, and this is for the state space description, and where each cell belong to a tracking area. So, each cell belong to a tracking area and each tracking area belongs to the service area, which is served by one S service gateway, and this is connected to UE and oblique packet gateway, that is PGW, and here your base station is having the edge node. Now, let us see consider the simple model, that is a one dimensional mobility model is considered, where the mobile user has only two possible destination, moving to a new service area with a probability p and returning back to the visited service area with a probability 1 minus p. So, let us say that this is so this is the user equipment. This is the user equipment, and this user equipment is moving to another service area, and now it is close to this service area. So, moving to a new service area with a probability p, this is a new service area with a probability p, and returning back to the visited service area, going back is with the probability 1 minus p. So, higher values of p indicate that the user is moving far from the current data center. Here there is a data center through which he is served, DC data center. So, the residence time of the user, that is the duration of users stay in a particular service area, follows an exponential distribution with a mean 1 by 1 upon mu. Hence, the service state and the state space S is defined as 1, 2, 0, 1, 2 and so on up to threshold. The threshold represents the maximum distance, that is in terms of number of visited service areas from where the service must be migrated to an optimal data center. So, the state represents the current distance of UE from the data center of the current cell, and that UE is located on. So, the action space of the MDP is defined as two dimensional vector, that is A1 and A2, where the action A2 is used if the service is migrated to an optimal data center, while action 1 is used if the UE is still being served by the same data center. So, here both the actions are shown over here in this particular model. So, FMC controller observes the current state, that is the distance of UE from the current data center of the network, and associate the set of possible actions, that is AS, to take it. So, taken upon the arrival to it from the previous state. Now, for a given action A, an instantaneous reward is associated to the transition from state S to another state S prime. Now, here when user equipment hands off from a particular service area to another service area, the FMC controller has to decide to migrate the service using the action A2 or not, migrating it using action A1. So, let us see this particular figure, which illustrates the Markov decision process for FMC migration decision making process. So, here you can see the direction of 1D mobility of the user equipment, that is 0, 1, 2 and these are the service area. So, if let us say that this particular service area has the that this is the A1. So, A1 is that it is being used if the user equipment is still served by the same data center, and you can see that there is also A2 and so on. So, all these actions are modeled over here using movement of using the Markov decision process. Now, in MDP, for each transition a scalar reward is obtained. The reward is a function of the cost of migrating a service, 0 in case of no migration, and the quality obtained from the new state. So, the cost of migrating a service is defined as follows: CM is the cost of migrating all the service or part of it. So, gain is shown over here, that is the reward point is nothing but a gain. So, the reward function is derived as follows: R is equal to QS that is state transition, and minus GA, where QS, that is the quality perceived by the user connected to the source data center from a distance S in terms of number of visited service areas. So, QS is inversely proportional to the distance from the source data center. This means that the farther the UE is from data center, the lower quality of service is experienced by UE user equipment. Note that the distance captured by state of the MDP. Now, for Q0, that is the maximum quality that the user equipment can obtain as the UE connects then to the optimal DC. Generally, the quality function can be expressed in the form of QS is equal to Q0 minus K, where K is a predetermined factor. Now, optimality equation. Now, let us say V of S denotes the maximum discounted total reward, and given the initial state S and given V s is equal to maximum of all those policy, where pi is nothing but the policy from the set of all policies. Hence, the optimality equation is given by V s, where is maximum of the policy, that policy which maximizes the overall factor. So, where gamma is the discounted factor, which is shown over here. So, solution of optimality equation corresponds to the maximum expected discount, total reward, and the optimal policy pi star achieves the maximum reward. So, that action which gives the maximum reward is being calculated here in this optimality equation. So, the optimal policy pi star S indicates that the decision as to which network and which data center the UE is to be attached and is connected to is given by the state S. So, there are several algorithms that can be used to resolve the optimization problem given by the above optimality equation. Now, the value iteration and policy iteration are the two noticeable examples using dynamic programming approach, meaning to say that we are now going to derive an optimality equation. The optimality equation is expressed over here, has two important features. One is the reward and the other is the discounted reward, the discounted factor. So, there are two things which is expressed here in this particular equation, and that particular policy out of several policy which is called the optimal, which gives you the maximum reward, and that is what is shown over here as V of S. So, that is called the optimal policy. What is that optimal policy which gives the maximum reward is called, that is defined using this optimality equation. Now, VM migration, let us see that VM migration process may further be improved by the mobility prediction, where we can estimate in advance the throughput that the user can receive from individual MEC servers as it roams throughout the network. Estimate the time windows when the user performs the handover, design the virtual machine migration management scheme, selecting the optimal MEC servers according to the predicted output throughput. The disadvantage of such a prediction model is that it requires huge amount of information in order to predict the throughput. Now, therefore, let us summarize this discussion. So, this particular discussion is the effect of VM migration based on the mobility prediction factor. So, if we somehow derive a process which is giving an additional information about the mobility prediction, let us see that how we can improve this VM migration. So, this particular mobility prediction may improve the VM migration, where we can estimate in advance the throughput that the user can achieve from individual MEC servers as it roams throughout the network. Then second is that it will be enabling to estimate the time windows when the user performs the handover. third thing is to design a virtual machine migration management scheme selecting the optimal MEC servers according to the predicted throughput. So, these particular two things are quite related, that is the throughput, if it is being predicted, then virtual machine migration management scheme will select the optimal MEC servers. Now, therefore, this particular mobility prediction will now estimate in advance about the throughput and also estimate about the time window when to perform handover. Throughput that the user achieves. So, two factor, and third, using that throughput it can also then derive that virtual machine migration management. So, mobility prediction has a important significance here in virtual machine migration, but the disadvantage is that to do this mobility prediction it requires the history or the data set. So, this advantage is that it requires a huge amount of information in order to predict the throughput. So, this particular throughput prediction requires lot of huge amount of information, that is called the data. So, once this particular data is available, then it can predict the throughput, and this throughput prediction can be now used here for VM migration management. So, VM migration decision process is further enhanced by mechanism that is predicting future migration cost with a specified upper bound on the prediction error. So, the main objective in this case would be to minimize the sum cost over a given time, and this includes finding the optimal placement sequence for a specific look ahead window T, which represents the time to which the prediction is done. So, a proper VM migration may not result only in execution delay reduction, but it also increases the throughput of the particular system. So, if the user is experiencing the latency or a jitter above the maximum tolerable threshold, the VM migration to a new MEC can be initiated. So, the selection of a new MEC server which is about to host the VM of the user is based on the required computing power and the availability of the resources at MEC server. So, let us see the key observations, and we conclude this lecture with the following observations. So, let us see about the resource allocation. So, the allocation of computing resources is strongly related to the type of application being offered, in the sense that only the application allowing the parallelization and partitioning may be distributed to the multiple computing nodes that we have seen during the resource allocation. Now, the proper parallelization and the code partitioning of the offloaded application can result in a shorter delays, as multiple nodes may pool their computing resources. On the other hand, the allocation of computing resources for parallelized application is significantly more complex. An increase in the number of computing nodes does not have to result always in the reduction of the execution delay. On the contrary, if the communication delay becomes predominant over the computation delay, the overall execution delay may even be increased. Hence, a proper trade off between the number of computing nodes and the execution delay need to be carefully considered when allocating the computing resources to the offloaded data. Now, let us see, using this particular resource allocation, let us see what we have to say about the mobility management, what we have learned about the mobility management in MEC. So, there are several options of user equipment mobility management if the data application is offloaded to MEC. So, there are two cases which we have considered. One is if the user equipment has the low mobility, then power control is a mechanism which can be sufficient to handle the mobility. That means, it is not going to do the handover if let us say the power control is being achieved at SCENBs in case of low mobility. This is true as long as the adaptation of transmission power enables keeping the user equipment at the same serving station during the computation offloading. However, if it is violating that the power is not sufficient to keep the user equipment at the same service station, then it has to migrate. However, if the user equipment performs a handover, the power control alone is not sufficient and VM migration or a new communication path may be necessary to comply with the requirements of the offloaded application in terms of latency. We have now understood that with a low mobility, it is through the power control we can avoid the handover, but if let us say that if it is power control is not the only sufficient criteria, then VM migration has to happen. So, let us see about the VM migration. So, the decision on VM migration strongly depends on three different metrics. So, VM migration decision means whether to migrate or not. It depends upon three different matrices that we have seen. The first one is the cost, that is called VM migration cost, representing the time required for the service migration and the backhaul resources spent by the transmission of virtual machines between the computing nodes. Then another criteria, another metric is called VM migration gain, that is gain M is the gain constituting the delay reduction, that is the data are computed in the proximity of user equipments, and saving of the backhaul resources, data does not have to send over the several nodes. So, therefore, cost and gain versus gain. So, we have to now see as per the criteria whether to migrate or not. So, the computing load of the node to which the VM is reallocated, since in the same situation the optimal computing node for VM migration may be unavailable due to the high computation load. So, there are these migration, these are the criteria which are going to decide about the VM migration. So, the VM migration is impractical if the huge amount of data need to be transmitted between the computing nodes and or if the backhaul resources between VMs are inadequate, since it may take minutes or even hours to migrate the whole virtual machine. So, this is obviously too long for real time services, and it also implies significant load on the backhaul, especially if the VM migration would need to perform frequently. So, not that time consuming migration goes against the major benefits of MEC, that is the low latency resulting in suitability of offloading for a real time services. So, what we have seen in this particular observation is that migration is impractical if the huge amount of data need to be transmitted between the computing nodes, and therefore, it can be if it is impractical, then it can be avoided. And if too long time for real time services is going to take, then also it is violating the QoS requirement or the real time requirement, then it is also implies significant load on the backhaul, and if the migration would need to be performed frequently. And note that here the time consuming migration goes against the major benefit of MEC. Now, let us conclude here this lecture. In this lecture, what we have covered two important MEC topics in MEC, that is the mobility management and resource allocation. Now, we looked at the important factors affecting the decision for application placement, such as application priorities, applications delay requirement and availability of computing resources that we have looked during the resource allocation. And we looked at some of the cluster formation strategies in MEC resource allocation that allows to reduce the time of task and power consumption of UEs. And we looked at some of the strategies for mobility management if it is low as well as the high mobility user equipments. So, therefore, we have also studied the mobility management aspects in the MEC. And what we have seen is the important paradigm for handling this mobility in MEC is the VM migration. So, VM migration strategies we have seen, and this VM migration strategy is used to balance the trade off between the VM migration cost and the migration gain. Thank you.